So our first talk today is Searching for Life on Mars. The speaker is Roh Bhartia. Roh Bhartia is a scientist at the Jet Propulsion Laboratory. He's been there for about 20 years. He received his PhD from USC in 2013, right?
Something like that, yeah.
Something like that. He is a member of the Life Underground from the NIA, run out of USC. Jan Amend is the PI of that, and he's the deputy PI of Sherlock, which is an instrument on Mars 2020. With further ado, here is Roh.
Cool. Thank you. Thanks, Luther. And thank you all and Vlada for inviting me to this. This is really cool. And get to talk about our favorite subject, searching for life on Mars. And I'm going to start off by stating that life exists in fractures. And this is something we want to get across to everybody here, is the way that life exists in the subsurface in these environments that are nutrient limited or in extreme environments are basically like by living in fractures. So I want to tell you things that you should take away from this talk, right? And I want to get you some few points here. One of the things I want to state is that life tends to clump in fractures and voids. It's not just a bunch of like a mass of microbes and bacteria basically spread out evenly over the surface. It's basically they're going through fractures and voids. And getting the spatial context combined with chemistry is necessary when you're doing detection, right? There is no one best method of analysis. Each technique has its unique capabilities and its challenges, right? So instead of saying, okay, well, I want to use this instrument versus this instrument, you want to actually combine the two. They have some unique capabilities by combining them. And we'll go into some of this as well. And then the other statement is, what targets, one of the things I want you to get out of the talk is like, what targets can you measure to search for life, and what are the challenges of looking at those targets? Like, how do we actually define life, and how do we actually go through and understand where, what you should be looking for, what one should be looking for, and the techniques associated to it. This is an image from Antarctica that actually kind of highlights the fact that that microbes and life exist in cracks. It's basically a crack of a rock from an endolith, so a slightly subsurface layer. And you can see these microbes are just basically hanging out on top of these little grains. They're about 1 millimeter in size, and they basically are just kind of sitting in the cracks and voids and areas. They're not spread out evenly over the area. They're basically just in clumps. So, what do we know so far? We have signatures of life on Mars, or well, what signatures of life do we have on Mars? And we started off by going to Viking, as Vlada was talking about earlier. And said, okay, well, we're going to go look for life in the way we understand it in 1975, which was a very myopic or naive perspective, which we were going to feed the surface with nutrients and see what happens. And there are 4 experiments that happened on Viking, and none of them were conclusive. What they did sort of suggest is that there was a highly oxidizing environment. So then we went back again to Phoenix, the northern latitudes, and ran another GCMS and had a sampling analysis system, and it basically also showed that there was inconclusive evidence of organics, but it did detect the oxides that were actually being observed early on Viking, and defined them as perchlorates using the electrochemical and conductive assay analysis of MECA. So more recently, we have Curiosity, or MSL, however you want to call it. And in this case, you have another GCMS, and you have this wonderful sampling system that actually shows that we do see organics. However, it's altered by the perchlorates that are present there. And so we have yet to, what we've defined here with the combination of the mineralogy from Kemen and the organic analysis from SAM, that this is an environment that's habitable. Right? And so that's what Curiosity is really defined, as well as with orbital assets. But to understand whether there's potential signatures of life, we have to go beyond just bulk analysis. And we have to actually understand how those organics and how those minerals are actually arranged. And so what Mars 2020 is doing is actually, think of it as a spectral rover, or a spectral mapping rover. And it has 3 different instruments on it. 2 of them are on the arm, which do high-resolution mapping of organics and minerals and elements. And one of them is on the mast to basically give you remote sensing of, or near-surface sensing of mineralogy and how it's distributed, and organics as well. So let me give you the importance of mapping for a second. So if you're going to search for a biosignature, one of the questions is, if you look at these samples, where would you start? And which one of these particular things actually has living systems in them or has a potential living systems? Now I kind of give you a cheat here. So this is a cold steep carbonate sample, subsurface ice from terrestrial environments, and Tissant, which is a Mars meteorite. But what's interesting about this is we still don't know where you would start by just looking at these samples. You could bulk all this stuff up and find organics and microbes in them and say, okay, well, we see them. But in Tissant, if you do that, you may find that you find microbes in it, but it's contaminants from the outside of the surface, or contaminants by just microbes crawling inside the surface. And so the question is, how do you actually target a potential secondary or tertiary analyses? And one of the things that we're pushing or talking about is actually how do you map. And so this is a fluorescence map of this carbonate, and what you see is that there's layer features here of organics, right? And those layers are actually humics that are in the that are basically in this carbonate. And the question is, it doesn't define life. It doesn't say those are living features or even that they were deposited by living systems, but you can now target your analyses to those locations. You don't have to look at the full bulk rock, right? And you can sort of say, okay, these are native, they're not contamination, they're actually associated to the rock. In the subsurface ice, these fluorescence maps are basically, again, showing you where you should target something to go to further analyses. And then Tissant, one of the nice things about this is that there was a large number of analyses done that were bulk that basically described a pyrimidine-like structure in Tissant, which sort of suggested there was hydrothermal activity in this rock or presented in this rock. And when using Raman and fluorescence analysis, you can actually see that the pyrimidine feature associated with this ring stretching motor in Raman actually follows a mescalinite boundary, which shows the pyrimidine most likely formed during a shock process or some slight heating with the small organics around it, and it formed pyrimidine at these slightly low temperatures. But it was done by shock. It wasn't a biogenic sort of formation. And so the power of mapping is pretty extensive or significant, and what we're trying to do is say, let's go beyond just saying, here's the inventory of organics, but how are they distributed? All right. So if we went to Mars and picked up a rock or went to the subsurface like we want to, we would love to see this, but that's not what we're going to see. So if we saw that, we'd be like, oh yeah, sure, there's life there. No, we're done, right? But it's more like this. And this is a sample from the South African mines. This is the type of SEM images that you get, and this is after hours upon hours of like scanning around samples from the subsurface. And your brain basically goes to, oh, those big globules over there are actually the organics, and they are carbon, right? But they're not the microbes. The microbes are these little guys over here, right? These little things. These little tiny ones are the same as these big ones. So what you're actually looking at is the majority of the carbon in this area is not microbial, right? The features are over here, these little guys, and they're pretty predominant. The sulfurous bacteria is like incredibly popular in the subsurface, but that's a different talk. But it gives you an idea that, first of all, microbes, they're clumps that they all kind of gather around, right? They're not distributed evenly over the surface. It took a long time to find this particular area. And then second of all, there's not a lot of them, right? All right, so we search for life through biosignatures. All right, so what is a biosignature? We always talk about biosignatures, potential biosignatures. And so to give you a quick definition, it's a substance as an element, isotope, molecule, or phenomenon that provides scientific evidence of past or present life. Right? So we have two methods that are generally stated as bulk analysis methods and mapping methods. And we've been predominantly in the community using bulk analysis methods because they're spectacular. They give you a lot of specificity in terms of the ability to detect a molecule of interest, a biomarker, and things like that. And so you have detection, identification of specific molecules, ratios of specific organics, organic inventory, so really spectacular capability. But you lose spatial context. You lose that mapping capability. So the mapping instruments, things like Raman, XRF, SIMS, SEM, EDS, microscopy, those are great at detection, identification of certain elements, and provide spatial distributions of molecules and elements and provides morphology combined with chemistry. However, there's catches to both of these, right? So again, it's not a matter of better or worse. It's just a matter of one does one thing and the other does another. And what a bulk analysis system does is it ingests a sample. So think of MSL. It basically takes a sample, crushes it up, and throws it into its backpack. And basically, there's an extraction process. It concentrates it and it detects material. And so What's awesome about it is that you can actually get these organics separated, and you basically, with this chromatographic methodology, and you allow yourself to get really nice separation of mixed species. You observe at very, very sensitive levels because you don't know where the organics or microbes or organics are distributed, so you concentrate everything around, and you basically get the capability to detect part per billion or part per trillion levels. However, as I keep talking about, you lose this mineral-organic spatial context, and that's a key point for understanding if microbes or if life exists in this environment. You also have cross reactions and alterations from the matrix are possible, as we see on MSL. The perchlorates do affect the system, right? Salts do change the ability of getting a particular organic into a phase that is detectable by some of these instruments. All right, from a mapping imaging perspective, it's really simple. You shoot a laser, pew pew, on a sample and you basically get a detection signal, and you move to the next volume. And I do mean volume, I don't mean area. And the reason I mean volume is because all these systems, whether the infrared or the UV, you get depth of the sample. Whether it's hundreds of microns or a millimeter, you still see a volume of material. And that'll be important in the next slide. But what you do is, again, maintain these organic spatial contexts, and you basically allow detection down to a single cell per volume. And that's the capability. You don't want to necessarily have to have a single cell per volume. It is very difficult. It requires a 100 micron sort of view of the world at a time. However, small volume analysis is a problem. You need to illuminate the material of interest to detect. If you're looking for something over here and the clump of microbes are over here, well, you're kind of hosed, right? You're not going to see it. It's not going to be in the sample or in your detection volume. And so you have to find a means by having a search criteria to say, I'm going to look at a sufficient amount of volume to actually see something. And then identification in mixed systems is difficult because what you're doing is you're taking a sample, illuminating it, and you're seeing whatever your particular methodology sees well, right? You're not going to be able to see everything, and you're not necessarily going to be able to pull everything apart from one another. And that's the challenge with imaging and mapping systems. You can increase the spatial resolution to the point of ridiculous, and you still have, at some point, something's mixed, right? All right, so if we take in the deep biosphere, and unfortunately Penny Boston's going to talk a lot more about this afterwards, and fortunately, rather, and I just kind of give you some numbers real quick. So in the deep biosphere and the subsurface ice environments on Earth, the bioload isn't the same thing you go outside and look at. It's not 10 to the 6 cells per cubic centimeter, it's 10 to the 3 to 10 to the 4 cells per cubic centimeter. Now, what does that actually mean? So if you assume a single cell, a fat and happy one at that, has about 200 femtograms of carbon in it, right? 1 picoliter of water for perspective. And a rock has a density of 2.5 grams per cubic centimeter. You can start to get a perspective. There's not a lot of material that you're looking for, right? So let me give you an idea. This is distributed in what the question is like, how does this material distribute? How are the microbes distributed? If they're distributed in an even distribution, right? So you have a cubic centimeter over here, then you'd have basically every half by half by half millimeter area would have 1 microbe in it, right? And so you'd have 10,000 cells in this cubic centimeter, and you'd only have basically, they'd be separated by half a millimeter. Well, in a bulk detection method, you don't care. Just chunk it all up, extract it out, and say, okay, here it is, right? And this is what we do for microscopy. For filtering for microscopies, we take a sample, spin it down, put it onto a filter, and say, okay, we want to see this area. But if you're trying to do in situ looking at the surface of the sample, right, as a cubic centimeter, you basically have to have single cell detection capabilities. And for a given half by half millimeter area, a cube, you need about 1,250 analyses to see 1 cell, right? But to see all the cells in this cube, you need about 10 million, right? So this is a very difficult situation, but this is not reality. Even distribution of microbes and organics are not what we see, especially in the subsurface. You see clusters. And all of a sudden, again, the bulk analysis is capable of detecting it, but you don't need the knowledge of, you lose the knowledge of like where those clusters are and what they're associated to. And for the scanning, you don't need the single cell detection capability because you're looking at clusters of organics and microbes. So the key isn't to say, well, throw the bulk analysis away. It's to actually say, use a scanning and mapping methodologies to find something, then take that particular locate thing and excise it and look at it with a bulk analysis, because the two combined are powerful, right? So to give you an idea of this life in fractures and voids, we have a ice core from Frixel. This is a glacier in Antarctica. And your eye immediately goes to this area, right, and says, oh, there's a piece of sediment there. There must be stuff in there, right? And you're like, oh, that's pretty good perspective. You can see it's actually in a fissure and a crack. And it's a good, it's a great starting point. We use visible images as a means to actually focus our attention. But again, if you use a technique like fluorescence mapping and Raman mapping, you combine them to see this, that the particle over here, the sediment, definitely have a lot of microbes in it and a lot of organics in it, but they're shooting out in all different directions, following cracks and fissures. And the point is that you're not necessarily just looking at this, you're actually looking at where they are and how they're actually surviving this environment and what they're doing. And so it's not that life is going to be evenly distributed. It's actually the fact that life is actually in fine locations and in clusters and points. Another example of it is in the subsurface area where you have cracks. Life in fractures here, you have 10 to the 4th cells per square centimeter on a fracture surface, right? The sessile population, those that are attached, is about 1,000x greater than the number of planktonic cells. Those are in the fluid, on the borehole water, right? So there's a lot more material sitting on the surface, and they're all in these cracks and fissures. And just for perspective, because of the nutrient environment in this environment, the nutrient source in this environment is very slow, the doubling time is also very slow. Like Ken Nielsen at USC has said many times, if you replicate in this low nutrient environment, you've just made a competitor, right? So you don't want to divide unless you really have to. All right, so to give you some idea about defining life and what do we look for, NASA's definition is life is a self-sustaining chemical system capable of Darwinian evolution. Well, that's excellent. I don't know how to detect Darwinian evolution. So what we do have an idea about is we know how life is on Earth, right? We know it contains DNA, RNA, proteins, fatty acids. It's got key biosignatures like hopanes and isotopes and things that everybody can sort of put their finger on and say, I think this is a biosignature. And there's a lot of debate about that, and that's not the discussion I'm going to have today. Just saying that we know what life is on Earth, and we should be looking at things that are associated to these, and we should look for biosignatures. But one thing to note is that we're continuously learning about life on Earth, but we're also continuously learning about abiotic systems on Earth, and how abiotic systems can mimic life, and how confusing the two can be, right? So it's not just to know how life exists on Earth, but how natural systems or abiotic systems can actually mimic life, or what the differences are. There's a non-Earth-centric approach of life detection as well, which is more of a general perspective. Say, okay, I'm not looking for a particular molecule, I'm not looking for a particular biomarker because I don't know what that particular life on another planet may be. So I'm going to say, assume life is not the only solution, that there may be another set of amino acids, or maybe another set of molecules that actually, instead of nucleotides, you have different sort of means of like creating a memory or a data storage system. So what you're looking for are detecting patterns that are indicators of life. Again, you're not doing one or the other. When you're doing life detection, you should be doing both. Your systems that you put together should not necessarily say, I'm only looking for DNA, RNA, because you'll miss this potentially. And if you just do this, well, why wouldn't you do this? We know how to do that fairly well. So, all right, so the astrobiology community has put together this thing called the Astrobiology Ladder. And it's actually on the NASA website, an astrobiology website. I think it's a in development process, and you can go to it and add your favorite instrumentation, your favorite methodology, and what the Excel spreadsheet or the spreadsheet as there shows is a general set of like capabilities or measurements, and it talks about the benefits of problems or challenges, and if they're how well do they do life detection, and everybody should be able to fill this type of thing in. So. One of the things they call out is growth and reproduction. So what do we mean by that? So I'll give you a sort of perspective of this by this movie from Mo El-Najjar's lab. So this microbe basically sitting there all of a sudden shoots something out of it, right? It's basically a nanowire that's just shooting out of it, right? This is really cool. But if I see that, I'm pretty sure, especially since I know these are protein stained, I'm pretty sure I'm not going to be confused whether that's living or not, right? The probability here is that it's life, right? So this is something that's an active process, and this is using labeled fluorescence microscopy. If you, well, that's cute. So in a metabolic sort of mentality, you have this, this other image that basically shows Shewanella consuming a manganese oxide, right? And this is not real time. This has been definitely accelerated, but it's about 100,000 to hundreds of thousands of times faster than abiotic processes for reducing manganese oxide, right? So the microbe here catalyzes life here. It catalyzes the reaction to reduction. And again, you would see this and you'd say, okay, I'm seeing a process over time that is happening, and it's got to be a living system, or it's likely a living system. So it's a high probability of living. This is using time-lapse DIC, or differential interference microscopy, but you can, for ancient record mentalities or rock record mentalities, you can basically use SIMS, like to actually understand the redox of gradients and see metabolic activities. All right, so you can go into the other part. These two in the ladder are basically pretty definitive life, right? I can see that, I can see in action, and I'm going to say that's living, all right? As soon as you get to functional molecules, you're saying that I'm looking for life that I know exists on Earth, right? And so what you have are things like DNA and proteins, and the techniques you have are the whole omics, the genomics, the proteomics, or methodologies, the mass specs that are out there, the Raman systems that can be used in some cases, infrared, CE. These are methodologies that can see these materials and easily say, okay, here's the presence, or even sequence them, right? And if you see this, you would say, okay, well, I have a microbe there, or something that's living. It's the way it looks like life as we know it, right? What you also can go down to further down the rung of the ladder is basically potential biomolecule components. So if you're looking for PAHs or fatty acids, or again, these biomarkers like hopanes or amino acids, these are systems that you can see that do exist, but they do exist also in meteorites, right? So you can get like a meteorite sample with a bunch of PAHs and amino acids in it. Murchison, for instance, had 75,000 different species of organics, right? Just naturally formed. They aren't formed by any sort of like biogenic sort of process. And so what you're looking for are trying to find features like hopanes that's maybe a unique biomarker, or other features that are unique biomarkers, but again, you're looking at the component and sort of trying to extrapolate back up to what it was at one point. All right. And these general indicators are more generic, right? So chirality, for instance. All right. Well, chiral molecules are used. There's a preference in the right-handedness or left-handedness associated to the particular microbe that you have, or the particular life you have. You typically generally use one. So you look at that racemization aspect, and if you're looking at organics on a natural system, or something that's abiotically driven, rather, you'll get something that has a distribution of organics that's thermodynamically driven, right? And life utilizes a particular set of organics. That set of organics, you don't have to know a priori, you just need to know, if you do an inventory, that there is a select organic set. If you look at basically elemental abundances, you can see variations and say, okay, look, there are features associated to there was layering associated to the sample that created a gradient that isn't naturally occurring, should not be naturally occurring. That was most likely microbially mediated, but definitely not necessarily definitive. In this particular case, you have a Raman map of showing minerals and organics, and you're saying, okay, the organics follow a particular set of veins, and the probability is that this is layered through some depositional process, but I don't have definitive light detection here. Again, this is a more generic sort of, I see a phenomenon, I'm interested, let's go further and detect something. Let's use this to detect whether there are other features associated to it. So this allows you to do stuff with mass spec, liquid chromatography, XRF, Raman mapping, and those are sort of general indicators. All right, so all these particular organics that we talk about are awesome because they can be both. So the organic detection that we have to determine whether there's life basically comes from a couple different methodologies. One, you can get abiotic synthesis. Other one, you can have life. And so from a abiotic synthesis, you basically have meteoric infall that have, or natural planetary processes that basically have pHs or amino acids, nucleic acids, is basically chemistry gone wild, right? On life, you have a very organized sort of set of chemistries, basically these microbes, proteins, DNA, amino acids, nucleic acids, fatty acids, but all discretized, right? Well, that's excellent if you're looking for extant versus like native processes. But then you add in some time, pressure, and heat, some geological time, pressure, and heat. You throw in a bit of cosmic radiation, some UV radiation. The UV radiation would be less if we're doing subsurface, obviously. And then you basically end up with an altered product, right? So this is a problem because now you're not just looking at necessarily the organics, you're looking at some altered product that may not be in where you expected it would be, right? So it may not be an organic that actually is in place, and I'll show you an example of that in a second. But to highlight this, one of our postdocs, Greg Wanger, basically took a sample of a cyanobacteria and said, okay, at room temperature, this is what a top sims looks like, right? And so you have a bunch of great organics that are very indicative of life, right? At 129 degrees, you kind of lose some of it, but you still can say that there's something there. And at about 200 C, you end up with just pHs. I can't tell the difference between this material and that of what was actually from meteoric infall. So this is the challenge that we have. How do you take this and deconvolve it to say it was this, right? All right, so to give you another perspective here of the power of mapping, utility of mapping, in this particular slide, what you're seeing is a stromatolite. When you look at it, it's an ancient stromatolite. Basically, if you map it or image it in SEM, you see these very microbial body-like sort of features, right? And if you do isotopic analysis, you get additional features that state that it definitely is. There are redox gradients here, and this was once a living system. Now, this guy from the South African mines, again, is an oddball. You'd assume, because you got a Hopane signature there, is that there's a biosignature of a circular-looking feature, right? What actually is the story here is there used to be a biofilm. That biofilm migrated through the rocks and fissures in into the subsurface, interacted with uranium, radioactively pyrolyzed the organics, and created basically encasing of this, right? These are not microbial signatures. They're basically a means by which it trapped the organics and ensured that there was survivability of the organics. But these used to be elsewhere, right? So it's the presence of the fact that you have hopanes and the CN carbon and nitrogen features that you can say that this is a biosignature. But it's a biosignature that was formed in some place, then migrated, and then was basically trapped in this unique environment. And so the point here is that the mapping gives you a story. The mapping gives you a story is to actually deconvolve what exactly actually happened. And it's the power of combining mapping with spectral analysis. All right, so in conclusion, I hope you understand that life tends to clump in fractures and voids. There's some key point, and getting the spatial context combined with chemistry is imperative. There's no best method. Leveraging the clump nature of life to coupling imaging life and coupling imaging to bulk methods rather is the ideal choice. And use both terrestrial focused targets, DNA, RNA, proteins, amino acids, as well as non-Earth-centric approaches to search for life. But there's challenges even then, right? What do you do in altered states? So that's all I've got. These are my acknowledgments. I would like to really thank the folks in the Life Underground effort, the P-STAR and the M2020 Sherlock folks to actually put all this stuff together. There's a cast of thousands. I will not go through all of them, but any questions?